Hello, everybody, and welcome to Memgraph. I'm Ani, the content manager at Memgraph, and I'll be moderating today's discussion. I'm here with our beloved co founder and CTO, Marco, and a very special guest from Weaviate, a leading open source vector database. Let's welcome Connor.
Hey,
Uh,
thanks for having me.
Welcome.
Thank you so much for joining us. And for those of our audiences who don't know you yet, can you share a bit about yourself and what you do at Weaviate?
Yeah, sure. So I'm a research scientist at Weaviate, doing a few things. I spend a lot of time studying information retrieval and search broadly, and recently moving deeper into the approximate nearest neighbor search stuff. So I've been at Weaviate for roughly a year. So I think hopefully enough to share insights about it. Did a PhD in computer science where I focused on deep learning, and I had a YouTube channel where I was summarizing deep learning papers. So, I came into Weaviate from a very deep learning first kind of perspective, and so that's kind of mostly where my head's at with these kind of things.
That's impressive. Thank you. And as you might have guessed, Marco and Connor will be sharing insights on vector databases. So the vector database space is so hot these days, particularly in the context of AI, machine learning, LLMs. Let's talk about where that's coming from. And let's start by hearing both of your perspectives on the importance of vector databases and how they differ from traditional database solutions. So Marco, do you want to go first?
I can explain my understanding of a vector database. I think it's critical for these machine learning and AI applications to have something like a vector database because in machine learning you often represent something as a vector in some n-dimensional space, and then you often deal with a lot of these vectors, and vector databases help with exactly that. The question is how to fast search through these things and how to do different machine learning tasks. And then there is a special type of database which does exactly that and helps with these searches and has a bunch of features about how to do that in a very scalable and performant way. Maybe Connor, you can explain probably not much more details.
Yeah, good. I think kicking it off from the high level motivation that we hear all the time is people coming from this world of like keyword search, and now they're coming into semantic search. That's like the most common evolution story of this, I think, where, previously if you wanted to find the Eiffel Tower in Paris, you'd have to search Eiffel Tower in Paris, and that keyword would have to match exactly, that would have to be exactly contained in the documents you're searching through. Whereas now you can have landmarks in France, and you can put that into this vector space, and then the vector distances will still find Eiffel Tower in Paris. So that's like that's like the evolution of search technology. And then, what you mentioned about vector representations of data in machine learning, and machine learning models, there's different kinds of machine learning models. There's classifiers where you take something like an image or text and you produce a label for it. And then there's generative models where you try to produce images, or now we're seeing with the language models where you produce text. And then there are these embedding models, and embedding models are, I think, actually a pretty new category of machine learning models where you directly optimize for these vector representations of data to preserve semantic similarity between positives and then push them apart from negatives. And so it's a pretty interesting new optimization task where typically when we're talking about these embedding models, we don't just mean like slicing the 10th layer out of 12 of a generative model and then using those vectors to embed data. We're usually directly optimizing for these embeddings that capture semantic similarity. And so this is a pretty interesting thing with just respect to the machine learning background of how you optimize these. Obviously in text, you achieve the semantic similarity, but then if you also step into like images, audio, video, there's like no other good way of doing this. They would have things like, color histogram features that would describe images before this kind of put it into a convolutional network and optimize for the vector embedding to preserve the similarity between two dog images. So it's a really novel solution for those kind of data types. For text, it's also quite interesting with how you move beyond just keyword matching. But yeah, I don't know if we want to continue, if you want me to dive into the details of once you now have all these vectors, how do you then what is now the vector database technology? So I can continue on. So
I like the maybe I can jump in. Maybe I like the analogy with text search. But I think concept of a vector database generalizes search in general. So you can search through any digital content, because like text search, it's quite easy to search for text. But you have if you have image, sound, or something like that, that's not easily representable by, I don't know, something simple. You need to have these vectors, and then you're actually searching through that space of, I don't know, a video or something, video content. Yeah.
Yeah, exactly. And it's such a universal interface. Like even, graphs can be embedded into vectors, and, like say it's like a neighborhood graph or a social network graph. And we'll get into the details. I think there's all sorts of interesting things to talk about with that. But maybe just finishing the pitch on the vector databases quickly. The next big thing is then you have like a billion of these vectors, and you want to then compute the similarity between your query and the documents in your collection. And so you don't want to just vector distance a billion times. So instead you build up this data structure, this HNSW proximity graph, all sorts of optimizations behind, compressing the vectors with product quantization, things like this, where that's how you then scale it and, get this super fast search on enormous collections of data with, as little memory overhead as possible.
Interesting. And fast search is one thing, but what would be the other more specific use cases that Weaviate has come across, or in general in vector databases?
Like in addition to search is easily the big one, especially with now the retrieval augmented generation with the language models, and that's what's caused like the latest boom. I imagine also some of the graph relation stuff can benefit from this, as well as things we'll talk about. But like that kind of taking a prompt and turning it into a query, and then retrieving specific information, like searching for your specific information to put in the input, to then have like, GPT-4 reason about your data without needing to train GPT-4. That's like the biggest application that's causing like, it's just like kind of like chatbots is being realized, and the application of chatbots is just massive, because you could take just like anyone who's working with information of any capacity and just take like their documentation, like if it's, whether it's like if it's like legal contracts, you can just easily apply this kind of framework to have chat over contracts, or if it's like code documentation or laws and policies, just like any kind of information, you can easily plug this in, and now you have like a chat bot. And I think it's hard to undersell, like, I think chatbots, like, just they're going to be one of the biggest applications of AI. It's like self-driving, it's like medical, it's like one of the biggest things you can think of, I think, really. So that one is super powerful. Recommendation is also a really interesting one, because recommendation is super similar to search in spirit. Just like instead of having an explicit query, you have to imply a query for the user, and it becomes an extremely similar, computational problem. There are like other things you can do with vector embeddings, like say cluster analysis, like topic modeling, or say outlier detection, or you can use it in training deep learning models for say data deduplication, or like active learning, where you try to like find high loss regions and prioritize training on those. So there are a few other applications of vector embeddings, but I'd say search is the one that's causing it to take off.
Thank you. And for those exploring the opportunities in the market, Weaviate is definitely one of the top solutions available. So what would you say are some of the important considerations when choosing a vector database, and what are the advantages that Weaviate offers to its users?
Well, without being like too adversarial to everyone else in the club, but like the open source nature of it, I think, is quite nice, because there's like a pretty active community, and we prioritize this Slack group heavily. We've also started like a forum where you can have questions answered by not only just us but also other members of the community, and seeing that happen is quite an interesting part of open source that helps that kind of take off. So the open source part is pretty interesting. I think another core differentiator of Weaviate with other vector databases is the module ecosystem, where so when you have a vector database, you build up this vector index, but you also need to deal with some kind of container for vectorizing the queries. You send in your text query, and you need to turn that into a vector, and you need to have a model inference for that. So we manage these like containers. Like if you want to self-host it, we have like in the open source thing, but also in the spirit of a lot of what happens is you outsource that vector embedding to like OpenAI API endpoints, Cohere API endpoints, Palm, Mosaic ML. So we orchestrate that API routing, and it's written in Golang, which is like a really good language for this kind of like concurrent API request control. So like whether you're vectorizing the query or you're then taking the search results to send to the generative model, we orchestrate this kind of model inference for you. And that's like another unique part of Weaviate. And then obviously every single vector database is going to tell you that we're all competing as hard as we can with respect to like, HSW optimizations, product quantization, scan, everyone's racing to do these things. So, there's ANN benchmarks, which is where the open source companies compete to demonstrate where we're at with this kind of thing. So that's also something you won't get from closed source. I don't want to like go too into that, but like it is an open benchmark that these companies are racing to see how many queries per second can we deliver and how low of a memory overhead can we, do it in an open way.
Interesting. And can you share some of the best practices to consider when implementing a vector database?
From our perspective, or from someone who's setting up their Weaviate instance?
For someone who's setting up.
Cool. Yeah, I mean, like, I guess the thing that we see all the time is in this, I think actually this comes a lot into why I'm so excited to have this chat and talk about graph relations and stuff, is because we like how you involve structure within the vector databases is quite an interesting topic. Right now, what we have is like a class design where, you have a class and the class can have properties and you choose which of these properties is going to be vectorized to represent the data object, the instance of this class. You can have cross references where you join classes together. So like, person attended school, and like these are two. So each class is its own vector index where you don't have any intersection. Or what you could do is within the class, like, say I have a person class and I have like job and research scientist or doctor, lawyer. These could also be symbolic properties that you can use to filter the traversal of the proximity graph. So what that means is whether you want to separate the vector index, is whether you want to separate your data into two separate indexes where you would search each one separately, or if you want to just design some kind of schema where you can filter the traversal and just build one index. And so I think it's quite an interesting topic. And so that's the first thing, is like just designing your data schema and being mindful of that. But then the second huge thing, especially with text search, is chunking your text. So embedding models, they're limited where they can only take about 512 tokens as input, which is about like 2 paragraphs. And so you have to be clever about how you're going to chunk up your text. If it's like a legal contract, or like let's say it's a code documentation or something, you have like a list. You don't want to like split the list in the middle, if that makes sense. Or if it's like a new title, you want to call that a new chunk, even if it's only going to be 100 tokens in this chunk. So it's not necessarily just you slide that 500 token window across your data. You be more clever about how you do it. So I'd say those are probably the two things, like how am I going to design my data schema, and then how am I going to chunk up my text, and then you're probably good to go from there.
Marko, anything else to it? Yeah, go ahead.
Yeah. With graphs, that's what the first thing you explained. It's kind of, you refer to a class, but I think that's equivalent to in the property graph to a label. So like there is a certain label of that you can put on the nodes, and then you design your schema by that. But then the question is, how do you refer to like what are the relations between these classes or whatever? And for that you need some kind of truth for that. So you have to express that somehow. And for that you need a graph structure to actually express the schema, and like adding a bit more meaning to these vectors, and how do you separate them and like put them in some buckets which should be explored then. That's kind of a graph problem or something. Graph is a good model to model that.
Yeah, I think, and so firstly, thanks so much for sharing the graph database 101. I'm still kind of catching up with the terminology, but so labels and then properties in the world of graph databases. Labels is like a special kind of property. Is that, and then because you also, so nodes is the key abstraction, right? Like each thing is a node, and then but nodes also can have data associated with it. Can you help me understand labels and properties a little more?
Yeah, that's that's specific to the property graph model, but no, there is key elements are, let's say, nodes and edges, or vertices and or edges, Someone referred to edges as relationships, and each node or edge can have a set of properties like a small key value store. So you can store data into these both nodes or edges, and then the label is kind of like a tag. So it's not a property. It's you can put arbitrary amount of labels to a given node, and you are tagging these things or like classifying what which node is what. Most of the implementers out there have a free schema, so you can put arbitrary tags on these and labels on nodes. It's not that you have strict schema definitions over it. Even though for some applications, obviously it makes a lot of sense to have the schema on top of that, and you can refer to you can start designing the schema as well and defining the schema. There is actually the whole effort on the query language side to define the schema like that. So let's say a person node with label person has first name, last name, and age or something like that. That these are required fields for a person. And then edges, there is in the strictly speaking in the property graph, edges have exactly one edge type, but that's also like a tag on an edge. So I know something like a weight or is connected, friend of, and stuff like that are edges.
Fascinating.
Oh.
Yeah, I think there's so much to that, like the weight on the edges, because it makes me think you could have embeddings for relations to, I think we'll dive into that further as we progress on the conversation. But yeah, it's so fascinating learning about the similarity between the data models. But I guess just probably the concluding thought on what's different about this with vector databases is when you have one instance of a person or like a like a book chapter or like a blog post or something, you're then going to put like 1 million or 100 million billion instances of that. So that's kind of, I think the key difference is, the one instance of your object, you're building up like a huge index of how much of that you have rather than true.
Yeah. I mean, that's a specific, I think, application, let's say in combination with vector databases. But like maybe I can explain how I think about the graph and vector, because with vector database you can search throughout all this space very efficiently, but like graphs can come on top or like however, but can give additional context, because you can have for a certain digital content or something, you can have like a direct relationship with other content, and then you can traverse through that content more easily, because it can give you like a strict context for each entity, and then you can guide your search by that. Let's say that's one example. The second one is probably, I think it's possible to prevent in these LLM applications hallucination, because often like a model doesn't know about the actual meaning or what's the truth, because truth is also different in different contexts, and then there's someone has to be stored what is truth, what is the source of truth for these things, and then for that you need some data structure to express that, and the graph is very convenient for that.
Yeah, I think with kind of two things to what you just said, like the first thing of the source of truth and updating something like, was born in 1996, and then you're like, oh, wait, that wasn't correct, it's 1992, and then you have that easy way to update. Whereas if you just have a vector index of text updating it, I don't really see how you're going to do that. I have no idea how that's going to end up working out quite yet. But then that other thing you mentioned is about if you want to compute feature, we talked about this quickly, like computing features like page rank or centrality or betweenness, like this, like graph analytics particularly. And I love that you brought up the like a blog post cites and other blog posts, or, like citation graphs and stuff, and computing those kind of features is super. Like coming from the world of search, I think of these features as being like attributes in like a tabular data frame that would then go to like XGBoost to like rescore the items based on these features of like. So first I take a semantic query, like I don't know, I like the landmarks in France thing, and then I have all these search results for different, Eiffel Tower is one of my search results. I don't know too much about France, but like other landmarks are in there, and say like this blog post about Paris is like so well linked that it has this page rank score that is like saying this is a really really connected blog post. So then you would re-rank it to the top. There's a better example out there of that.
No, for sure. But these things can, like centrality of a node or some community of a node that can be easily calculated and then incorporated in I mean any machine learning task or work.
Yeah, but computing it like with it, and I think that's why you need a graph. I think that's why it would make sense to combine Weaviate and Memgraph, is because Weaviate I don't think would be I don't think it'd be easy for us to compute those kind of metrics from your data.
Yeah, I mean there are multiple ways of doing that, but I think the really hot topic in the research community recent years is are these dynamic graph algorithms which operate on like streaming data and are producing some approximative results, but with that large space you have to compute and process. It's very time consuming, and with a lot of these dynamic algorithms you can do that like super fast and scalable in a scalable way, and then these things can be used like down the pipeline.
Yeah, maybe if you don't mind taking that, like I read a bit about breadth first search, like graph traversal algorithms, and I mean we also use graph traversal for our proximity graph searches. Can you tell me more about like the optimizations between I need to compute centrality for a node? What do graph databases do to optimize that?
Yeah, I mean traversals are the, I would say, basic workload type for a graph, because you have to explore like a neighborhood of a node, and then you conclude something. For example, you detect fraudsters in a specific use cases. You detect fraudsters, but you do that by traversing a neighborhood, just going through these edges and collecting interesting data, and then having some. I mean, you can build all different things of all different sorts of engines to detect fraud, but just going around, and then. That translates well in these, let's say, calculating centrality or PageRank on a node. Usually, that's like a proper algorithm is just to go through all the nodes and iterate, I don't know, 100 times throughout everything when until you converge the algorithm, when you get the results that don't change anymore. That's kind of canonical implementation of a PageRank. But the dynamic implementation is actually based on traversals and building these embeddings, or like traversing the graph and calculating the scores in a random way, let's say throughout the neighborhood, and then doing the same calculation, but just not on the whole graph. Instead, you calculate on a neighborhood, and then that's where these traversals, making them, ensuring that they are super fast. That's when where graph databases are like interesting, because you have these connections between data points kind of stored in an optimal way, and it's optimized to do fast traversals over the place. And then on a scale, like you optimize for executing these things a lot of times and getting the values which are okay. Does that answer the question?
Oh yeah, for sure. Yeah, I mean, I've learned about like like you have like a Markov chain where you multiply it out until you have a steady state distribution to calculate PageRank compared to traverse, like a little bit of it. But it's making me, there was another thing that I saw when I was reading about Memgraph, which is about these node to vec features, and you mentioned embeddings. Can you just tell me like more about generally how you see like node embeddings and how that fits in this picture?
I mean, yeah, my usually my view on this is that, yeah, you have a node and then you calculate some embedding based on something, so you somehow come up with an embedding. I mean, the function there could be anything, and once you have an embedding, which is a vector, so with that vector you can do other stuff. So you can try to find a similar node. That's kind of an opposite, I think, use case, because somehow you make a representation of that node, and then you use that representation as something that can be easily plugged into a machine learning model. So that's kind of, but all these, the function is kind of, I mean, from the Memgraph perspective, we are trying to offer tools that for developers where developers will easily define the function and define what is actually an embedding. And then once you have that embedding, the question is, what do you do with it? That's kind of completely arbitrary from a graph standpoint.
Yeah, I mean, I've heard about like, so I've heard about things like deep walk and node to vec where they're out. So it's like, as I mentioned in the beginning, the new thing is that we take two positives and we try to make their vectors similar by optimizing them with deep learning models. Where deep learning models, they're called deep because they process it in like several layers. So like at layer 10, it produces a vector. That's the output from the model. And then, we're aligning the positives. So what I like about the graph is you kind of have this notion of positives. Like say positives are like 1 hop away, and then a negative is like 8 hops away or something. That's what I think is the basic idea of like deep walk and no tvec, is you do random walks along the graph with like, if you have like 3 random walks, and that's going to be your positive, whereas like 10 random walks. So yeah, maybe that's something that I think would be another interesting thing about graph databases, is you can sample that kind of data faster because you're just, yeah.
Exactly. So, I mean, yes, and then like all that is based on these fast traversals, random fast traversals through the graph, and sampling, some way of sampling of a graph. And yeah, for these type of things, graph database is really optimized because you have these connections, you have pointers, and then you are searching through the neighborhood. That's exactly what is the use case for a graph DB. And if you're doing that randomly, then it means that you don't have to usually problem with any type of even like SQL databases have a huge problem when you have to join every table, multiple tables. And with the graphs, if you are traversing a neighborhood and you don't filter out, that's like a exponential problem. You are just collecting a lot of data. You are traversing a lot of nodes, and it becomes really infeasible super quickly. But with random walks, you are aggressively filtering because you're jumping to exactly one next node, and then you just let's say collecting one traversal, and that's it, collecting one path. And for that type of thing, is graph is really optimized. So yeah.
Yeah. Yeah, I think we totally agreement of that. And I think that other thing, like you quickly mentioned, like the joins with SQL, that's how I understand this kind of like graph, the evolution of graph databases is about some of these like queries that, like if you're like a payroll software and you join all these tables together, that like that is so that is really suboptimal compared to just traversing when you only have node relation entities. Can you tell me like a little more about that story, like the SQL graph database kind of?
I mean, yeah. I mean, a hop in a graph is a join in a relation, exactly that, like it's exactly the same. And you have similar problems with in graph databases as you have in the relational. Of course, you have that usually implementations are done by having the pointers, so you have a little bit more data, so you can faster, let's say, traverse or join. But pure complexity on the data side can be a huge problem. And I mean, there is not good if you have to join like 10 tables or something, which are huge. That's a problem for any system. So only if you can easily or fast filter the result space, that's really really good. Yeah.
Yeah, super cool. Yeah, sorry, I kind of lost my train of thought, but I was thinking a bit about the SQL thing. So I'm pretty satisfied with my understanding of that topic. I think it's obvious that the graph database offers faster joins in that kind of way, and with less overhead, not needing to bring these big tables together. But the question that I have about graph databases, and I think large language models, I think this is going to be a nice discussion topic, because I think large language models do kind of offer like a way to facilitate the maintenance and the entity linking of creating knowledge graphs, is like, that problem of like, I have like, because I think a big reason why vector databases are doing well is because of the way that you can structure unstructured data with vector embeddings. You can just give me a new article of text, and I can just index it. Like I don't need to like extract all the relations from the text. So yeah, like how would you say about the the maintenance of knowledge graphs and entity linking and all that?
Yeah, I kind of have two thoughts. So maintenance is kind of super hard in the graph, because you have to know what do you maintain, and that's why I guess maybe one thought is that usually these usually graph databases are not schema heavy, so you can do that on the fly as you wish. So whatever you want, it's not that you are limited in any way. So system shouldn't limit you in any way. But yeah, you're right. So like how I see the vector in all that or vector database, because essentially like a vector database is a fully connected graph where edges are computed on the fly whenever you do the search, because you find all the like the nearest entities or these vectors in the space, and then kind of, yeah, not sure, like these things are kind of have to be combined. So like ability to search throughout the whole graph super fast, and then putting some structure in place to, I don't know, maybe accelerate something, or yeah, defining the source of truth as we mentioned, and stuff like that. So having, at some point you have to define, yeah, this vector relates to that vector in a that way. So that's the truth, or that's the distance or something, like whatever it might be.
Yeah, like totally. There's no sense of, it's just the vector, but they just have this dot product. It's like 0.84.
Yeah,
So,
and that's super valuable. So usually, like similarity between things, like it's super valuable. But anything else, you have to kind of store that somehow and combine. If you have a query or a workflow where you like iteratively doing something through that whole space, for that you need to like somehow guide that search and probably store the results as well, because every computation is kind of, it's kind of also a way of caching stuff, because if you compute something once, you don't have to do the same thing next time. So yeah.
Yeah, so I guess it's like, I see like two ways you could design these graphs, where it's either like, node, where a node is like a super compact thing, like, if it's like chain of thought prompting, it's like chain of thought prompting, just that is the node, compared to where like say the abstract of the paper is the node, right? Like how much data you kind of bring with you about the thing. And then, because I guess the what I'm trying to get at is how you prompt, like how you can maybe prompt a language model to extract, like you give it the ontology where you just have these, the most compact representation of the nodes and edges and something, and from there, like it's kind of like ontology prompting to extract does that make sense?
Yeah, so like maybe a recent use case or things that people are doing. Usually when you want to like writing cipher or any, maybe that's a bit off topic, but writing any programming language or any declarative query is always hard for people. And yeah, even if you're a SQL developer, you have to understand like how to query a certain system. But with these language models, what's possible, you can type a query in your language, in human language, that can be translated into SQL or Cipher or any declarative language, execute that query against some system to get actual facts, which are actual facts at that point, and then translate that into something which is very usable by the language model. So you can have maybe a very dense and expressive result back, but that will be costly, because these language models are actually costly to run. Or you can have something very compressed, which is which has very limited but like required type of amount of information, and then you plug that in back to the language model, and then you get a response in the human language again, and by that you can actually make a lot of these interactions much more easier, and also much more truthful, because in a graph system you have like a source of truth or something, and you will get actually pretty accurate results back, because usually language models, if you ask something, you get something which is maybe not true, but if you just say, yeah, this is not true, can you repeat, like the model will get the right results. You just need a bit of help to figure out the correct answer. So
Yeah, well, I think this is a pretty deep idea. Like you mentioned that having like GPT-4 write a cipher query, that's kind of expensive to scale that out. Right? Because you could be talking about like 2 cents per inference for that, and then I don't know what kind of thing you're building, but and how much you chain it. But so, because I've been thinking about this idea of like, I probably should have mentioned when I'm doing my introduction to Weaviate that we have like a GraphQL API, and like it's also kind of like a domain specific language for how exactly you use the syntax. And if it's your first time using Weaviate, maybe you're still catching up with how do I query it? Similarly with Cypher, it's like it's tricky to figure out how to write Cypher queries. So would you think about training a large language model, a smaller one, like a 2 billion, and I think the open question is how small can we make these language models, but they still possess this kind of, they're still impressive. So like one that would specialize in writing Cypher queries. So it'd have some training data set, maybe that comes from GPT-4, but yeah, it's like a smaller model that writes Cypher queries.
Yeah, I think. I'm not sure, but I haven't run any experiment on that or did some analysis on that. But I think translating human language into Cypher or some declarative programming query language should be relatively much simpler than all the stuff that LLM can do and like these large models. I think that because usually it's very easy to declarative style of the constraint or a property which is there is that you just have to extract from your prompt what's like the syntax of that in the query language, and it's usually I want this and I want this. I have to translate it into match and return something. So that mapping is quite straightforward, except it's not, but it's easy to detect when there is no structure like that, I guess. So I guess much smaller model should be able to perform that task.
Yeah, I'm pretty optimistic about that as well. I mean, it's very similar to the text SQL stuff, right? Like we each have our own, like vector database. It's not like quite just you send a vector into the vector index. There are like other levers that you can pull and I think it's a pretty cool topic. I mean, the interface, I think especially with the world that you're in with the graph databases, I think that will actually help a ton because you have like this learning curve to RDF data schema and Cypher as like just that kind of thing. So I do think this LLM query parsing for knowledge graphs is super interesting.
Yeah, but I didn't know. You mentioned that generating Cypher based on that LLM model is expensive. So I wasn't thinking about that. I was just thinking about the second part, generating like the answer. So collecting. So because when you collect data from a graph, it can end up with arbitrary amount of let's say data out, and then that has to be pushed to a model, and that can be expensive. The first part is just like a small prompt or something, usually some like a statement or a question. And that's small in terms of running it, but yeah, that's a good point. How to actually what's the cost of all of that together combined? Because it's not only just I was just focused on the second part because it seems like it depends on the data set, but also the first part and overall cost might be interesting to explore a bit more. But yeah.
Yeah, that's I think we were calling that generative search is like our marketing word to write to the brains, but like this idea that the output of search engines is transforming. You no longer expect to see a list of search results. You expect to see it synthesize the answer and present to you the answer. So like what you meant, there's so much this is what I think like the LLM frameworks like Llama Index and LangChain, this is how I think they got started delivering value, is with prompts that so in parsing through search results, a common prompt would be this: please summarize these search results. You'll receive the search results one at a time, as well as the current summary so far. And then you just, template in where you have the local memory of the search results so far. For the sake of graph databases, I think what would be interesting is it's also called this map reduce prompt, where you basically, you have the question and you say, so you have the question where you template that in again, and you say, and then each of the noun, relation, entity things are turned into like a natural, or you could just keep it in the tuple. The language model is actually super good at reading like JSON or tuples. They understand that pretty well. So like you say like how many of these facts are relevant to the question, and then it would filter it that way, and then you aggregate the filtering, like you apply that over, like because you've retrieved like 10,000 facts, and so you apply that over each one in parallel and then pool it, and then that's how you keep doing this. But as you mentioned, that's crazy expensive. I don't see how that one gets compressed, because you need the general language understanding ability to make this so.
Combining, by just a crazy idea, combining graph embeddings or vectors by applying vector search to actually sort these results.
Yeah, exactly. Yeah. I mean, So then would each noun relation entity have an embedding associated with it?
Sorry, can you, it was a bit choppy.
Sorry, can you hear me now?
Yeah.
Okay. Yeah, so I've heard of this topic as well, where there are ideas of like, so there's always like retrieval and then re-ranking, where we use this analogy where it's like you're fishing and you like, okay, I think the green fish is in this part of the ocean, so you throw like a huge fishing net at it, and then you get like 5,000 fish on the boat, and then the fishermen manually inspect the fish. Is this the green fish? No, this is the green fish. So it's like the fishing net is like super cheap. You do graph traversals or you do vector search, and it's like here's a ton of candidates, and then you have some kind of like re-ranking strategy. And I think this kind of ID linking could be a way that you combine graph database and so you get all these facts, and then they have IDs that are associated with vectors, and then you like would vector search and then re-rank by having it be in the set of the IDs, and then inversely you get the vector search results, and then you take those IDs, hit the knowledge graph and stuff like this, but probably needs to be orchestrated with the language model.
Yeah.
And hopefully that was on
Interesting.
track.
Interesting. I have to digest a bit, but yeah, interesting thought, because you can leverage another graph to actually guide that processing of the results.
Yeah.
So go ahead. Sorry.
Oh no, yeah, you go.
Yeah, having covered the synergy between graphs and vectors, and one question to you, Connor: how do you see the vector database space evolve? What are the trends or predictions you may have?
Well, I think the biggest trick shot you can do is to say there are like two things to it. It's like to say like, hey, I put 1 billion vectors on this laptop, and then because you've done something with the compression of the memory overhead with that. Like it obviously then you need to say like with what latency sort of also, but like that kind of thing of like, I don't know, I hit like 50 millisecond queries with 1 billion vectors on this laptop. I think that kind of thing would be I think that kind of thing would enable a lot. But really, I think the thing that's emerging on the future is that we're calling this generative feedback loops, where as these language models get cheaper to run inference, or not even, let's say the generative image models, like you have the new DALL-E model, or let's say you trained a GAN on like 100,000 or like let's say 1 billion pictures and stuff, and you want to see like what kind of novel images it's able to produce. I think the best way to do this is you have to sample like 1 billion. With GANs, you pass in random vectors. It takes random vectors, turns it into images. So you have to like produce all these images, and then you embed them, and then you like see what you can like. I think you have to produce the output space to then inspect the latent space of those images with the contrastive model. So yeah, I think that's the thing that I'm most excited about is making like taking an LLM, pointing it to your blog post, and then just having it like write like 1 billion potential things that it can like think of and intersect with the post, and just like keep going, and then you explore kind of like what the ideas it has, and it like will create like more data, and hopefully, and then the vector search, that's the tool to how you see like what in the world has it generated, and is any of this useful.
This is kind of like embedded feeding loop. So you generate more content, and then you have more to search.
Yeah, exactly. And then it keeps retrieving. Yeah. So I mean, I also think the language models that write code and test the code, there's something to that. I think also. I don't have a great sense of it. We recently had a hackathon with a project called Code in It, which was sick. It was like this, it tests its code, it sets up virtual environments, just amazing. And there's definitely something to LLMs that write code and like plug themselves into open source repositories with pull requests and all that stuff.
Okay, thank you so
Imagine a code reviewer, which is LLM code reviewer, which is super nice.
Yeah. Yeah, exactly. Very understanding.
And my last question to both of you: is there anything I didn't ask but you're willing to share within this session before I end the event?
Oh, like an announcement kind of thing?
Or maybe in general about the topics that we discussed. So this is space for you to elaborate if there's anything.
Well, I guess I would say quickly, there are two things that keep me to this. So in Weaviate, we have this feature called ref2vec, where it's about you have a class and it has a cross-reference to another class, and we send embeddings through the classes. By far the most used application of this is user products and then user likes some products. So you represent the user as the average embedding of the products, and you recommend with that. So, but this general idea of sending embeddings through classes with cross-references, that's what always brings me back to this topic. There's an academic paper from Harvard Biomedical Informatics called Prime KG, and it's drugs, diseases, genes, and it has unstructured description. Like, so each gene has an embedding associated with it, and it also has it's linked to this disease and stuff like that. So that's also the academic work that just that's always brings me to this topic of graph databases and vector databases. How is embeddings going to use graph structure more?
All right. So once again, it was a pleasure having you, Connor, and thank you for providing this unique opportunity for also our viewers to explore graph databases from an expert perspective. And to those watching us, if you're interested in trending topics in tech, make sure to subscribe and let us know in the comments what you want to see next. And we'll see you soon. Thank you, guys.
Thank you.
Thank you both.
Bye-bye.
Really fun.
Bye-bye.
Bye.
Yeah, it's fun. Yeah, bye-bye.